So, today we're going to dive into something really cool, a totally new way of thinking about how artificial intelligence actually learns. It's a perspective that kind of throws out the complex algorithms, at least for a moment, and replaces them with a simple, really powerful idea that we see all around us, a chain reaction.
And to get us started, I've got to ask you a question. What in the world do falling dominoes
Have to do with artificial intelligence? I know, it sounds like a weird connection, but trust me, you're about to see how this incredibly simple physical process gives us a powerful new lens for understanding the very heart of machine learning. All right, so let's start with the basics. That chain reaction. You know how it works. When you push one domino, you're not just affecting that one little piece, you're kicking off a whole cascade of events. And really, any chain reaction, whether it's dominoes or something way more complex, follows this really basic pattern. First, there's a nudge. Some small change gets introduced into the system. Then, that change propagates, right? It ripples out through all the connected parts. And finally, the entire system settles into a new, stable state. So just remember that. Nudge, ripple, settle. We're going to come back to that. Okay, so how does this actually connect to AI? Well, some researchers are starting to reframe the entire process of learning. Instead of seeing it as a bunch of complex calculations, they're starting to see it as a system of falling dominoes, a process of change propagation. Let's take supervised learning, for example. You know the classic setup where a model learns from data that's already been labeled. Now, in this new view, every single time the model makes a mistake, that error isn't just a failure. It's the nudge. It's that initial push that starts a whole wave of corrections propagating through the entire model.
And this is the key takeaway, the big aha moment. And AI isn't just tweaking a few parameters here and there. No, it's a deeply interconnected system where one little error sends a ripple of change through its entire structure, just like that very first domino falling over. Now, thinking this way is one thing. It's a neat analogy, but if you actually want to build things with this idea, researchers need a formal language, kind of like a mathematical map to help them navigate these super intricate chain reactions.
In that map is something called category theory. Now, don't let the name scare you. At its core, it's just a field of math that's absolutely perfect for describing systems that are made up of interconnected parts. It lets you zoom way in on one component or zoom way out to see how the whole shebang works together. For AI, it gives us the precise language we need to describe how learning actually ripples through a network. And this is not some niche, isolated idea. It's a really fast-growing field. For instance, concepts like backprop as functor use this exact language to talk about backpropagation, the learning algorithm behind most neural networks, as a fundamental building block, or categorical cybernetics, which applies these same ideas to understand feedback loops in pretty much any self-regulating system. It's all about finding a unified way to see how complex things learn and adapt. So, within this new language of category theory, scientists have developed some really specific tools to track how information flows. And they have a great name for them. They call them optics.
Yep, optics. And you can pretty much think of them as a set of specialized mathematical lenses. Each one is designed to focus on the flow of information in a very specific way, which lets us see exactly how changes are moving through a complex system, and more importantly, why.
And this toolbox has a bunch of different lenses for different jobs. For example, you've got profunctor optics, which are kind of like a wide-angle lens, perfect for getting a big picture view of how data is flowing. Then there are Bayesian lenses, which are more like a microscope for modeling how a system, like, say, the human brain, updates its beliefs when it gets new information. And that brings us to the star of our show today, delta lenses. Delta lenses are the tool that was built specifically for our domino problem. They give us the formal mathematical language to describe exactly how a nudge, or any change, really, propagates through a system while it's learning. To put it simply, they are the mathematics of the ripple effect.
So, okay, dominoes, category theory, these optics. You might be wondering, why go through all this trouble? What do we really gain from thinking about AI learning like a bunch of falling dominoes?
Well, here's why it's such a big deal. This isn't just about creating another new algorithm or making a tiny improvement. This is a real paradigm shift. It's a more fundamental, and you could even say a more elegant way to understand what learning is at its very core. So this is the payoff. This perspective offers us unity. We get a single framework that can help us understand an AI, a robot, maybe even a biological brain.
It's systematic, letting us precisely map out all the effects from just one tiny change. There's an elegance to it, a more fundamental way to understand learning. And all of this could ultimately lead to more robust and predictable AI, systems that we can finally maybe understand and trust from the ground up.
And that leaves us with this really big, fascinating question to chew on. If learning isn't this messy, chaotic black box, but is actually a structured, predictable process of propagation, then what's the next frontier for designing intelligence now that we have a map of the chain reaction?